All right, so we're ready for day 2 of our Chapter 4 Lesson 1 lesson on what is. So we went through this slide yesterday and we talked about what the book was trying to teach us. And we talked about how energy is that item or that thing, that substance that has the ability to cause or to force a change. And we talked about how the air is molecules and something can happen to them to end up with a change. And that change we called transferred energy. So we talked about how the air molecules are constantly moving and wind is created because the temperatures are rising and falling throughout each and every day, and because our Earth is rotating on its axis and therefore experiencing fluid friction, which stirs up the air molecules as well. So the air molecules is the energy to begin with, and then it's going to become a force. And that force, once again, is the ability to cause a push or a pull. And that force is the wind blowing across the earth. When that force hits something like the wind turbine or the windmill there, it's going to cause it to turn. And it inside has a turbine that it's going to spin. Well, the turning process, due to the force pushing it from the air, which is the energy, that's what we're trying to talk about. How energy is transferred from one location to the other, and the 3 principles which are required. We also talked about then what power was and how power is a measurement of understanding energies, forces, and work. And we looked at the idea that both of these people were shoveling the same amount of snow, but one person used a shovel and one used a snow blower. And we went and down at the bottom, we looked at the math and we talked about how the amount of energy transferred, which had to be the same because it was the same amount of snow being moved, divided by the amount of time it took. And the snowblower will take you probably a fourth of the time, if not less, to do a job than going out there with that shovel. So now we're ready to continue on and get into page 110. So we have several different types of energies we look at, but we start out with the 2 main ones that almost all others can fit in one way or another. We start out with the idea of kinetic. And if you remember with Bill Nye, he was going kinetic, kinetic, kinetic. Kinetic means to move, right? So it's energy that has motion. It's a moving object. When I look at electricity flowing to light up a light, then that electricity is actually flowing through the circuit and lighting up the light, and that is also a kinetic energy. Generally, we think of things like, something flying through the sky. It's moving through the sky. It's kinetic energy. Or animals getting around like the kangaroo hopping. It's showing a kinetic energy because it's in motion. You and I can show motion. Some people like running. I think it's a little crazy myself. But some people enjoy it and they are showing motion. Or even if one of our favorite pastimes is bowling. Right? So I'm going to transfer my energy from my hand to the bowling ball and it rolls down in kinetic energy. And then it hits the bowling pins and hopefully knocks them down. Once again, a transfer of energy. So kinetic just simply means to move. So when I'm looking at kinetic energy, then I have to realize that there are 2 main things that are going to affect kinetic energy. And the book does give us a formula that we really don't use in 6th grade. You'll use in junior high. But I'm going to explain to you what it means and what the impact is on the idea of kinetic energy. So it tells us that kinetic energy is equal to 1/2 times mass times speed squared. So when I look at what kinetic energy is equal to, then I need to think and understand what we're talking about. If we have the question like, which affects us the most when it comes to kinetic energy? Is the mass going to affect it the most, or is speed going to connect it the most? So let's say during this dodgeball game that we have a dodgeball coming in and it hits him at 50 miles per hour. We have another dodgeball that comes in and also hits him at 50 miles per hour, but it's twice the size. Well, mass is going to cause an impact, right? It's going to cause a bigger impact if the mass is bigger, and that should make sense. But when I look at the other option, because we have mass and speed, and I have that dodgeball going 50 miles per hour, but then the next one comes in and it's the exact same size, but it comes in at 83 miles per hour. the speed is going to hurt a lot more than simply changing the mass. See, speed is always going to affect kinetic energy with a greater outcome than changing the mass ever does. And the reason that is when I look at it, the speed is squared. When I look at the outcome of kinetic energy, the speed has to be squared in order to figure out its impact or the work that it's going to apply. So speed is always going to have a greater impact than simply changing the mass. If you really want to knock somebody over, you throw the bigger dodgeball at a faster speed. Then you have an even greater impact. So the kinetic energy, though, is potential energy. And potential energy, if you remember back to the Bill Nye video, he had the water in the clear plastic container raised up in the air. And he talked about how it was potential energy just sitting there waiting to be released by turning on the valve in the hole. So we're talking about stored energy, something that's not displaying energy yet. So in this example, it gives us the definition that potential energy is stored energy held by an object because, and then it gives you some examples: relative position, electric charge, or internal stress. So the raised object, such as the lady with the cane, it has a potential energy. If it's laying on the ground, it's really not going to hurt you. But if she raises it up above your head and drops it, it's going to hurt you because it's then released. But the higher it goes, the more potential energy it has, because we know free fall is going to consistently increase by 9.8 meters per second squared as it's falling towards the earth. In the same way, if you have the bow and arrow, you have potential energy. It will do nothing, it won't hit anything, it won't stick in anything, unless I change that into kinetic energy by releasing it. So when we look at things like a rocket is just simply stored energy. It has potential energy. The flames have not been turned on. The fire pin has not been pushed. So it's just going to sit there. And as long as nothing changes it, it's just going to continue to sit there. In order to have an outcome, someone has to launch it off. A water faucet, it's potential energy. There's water right to the point where the handle is turned off. And it's going to continue to push in that one location until you turn it on. All it takes is for you to turn that handle a little bit and water is going to start coming out. And the more you open the nozzle, the more water comes out because it is a built up potential energy. But as long as it's closed, it stays potential energy. You don't have to worry about anything getting wet. If we think about puppies, like my big dumb dog at home, right? When he's sleeping, he has a lot of potential energy. I know he has a lot of potential energy because once he wakes up, he starts zooming around the house back and forth 20,000 times, acting like a crazy dog, right? But at rest, it's potential energy. When you're sleeping, you have potential energy. Once you wake up, then your energy, you make it into kinetic. Or the idea, once again, of the batteries. So batteries are stored potential energy, chemical energy. So we have these ingredients that are inside of the battery that are going to keep a charge and then give that charge to some kind of device that needs electricity to run. Batteries will then drain. We recharge them if we have rechargeable batteries. But if I never turn the object on, I never put the battery in it, I just set the battery on the shelf, it just stays there as potential energy. So when I talk about gravitational potential energy then, our book starts breaking it down into a couple of different types. And gravitational potential energy is exactly what it sounds like. It's how does the effect of gravity come out in potential energy? And we've talked about this before many times. If I hold something up over your head by 2 feet compared to 2 inches, the increased gravity increases the amount of ow that comes out when I let it go. So the potential energy is stored. If I stand there and I'm holding this red ball and I just wait to drop it, it has potential energy. If I was standing on the lower level, it would also have potential energy if I didn't drop it. However, because I'm higher up on that ledge, getting ready to drop it, it has a an increase in gravitational potential energy. Or if I look at sitting on a hill, right? Sitting on a hill, I could look at a small hill, I could look at a large hill. Or if I looked at the flat ground. On the flat ground, there is potential energy in this car. But if I raise it up on top of that hill, it's going to have a much greater gravitational potential energy. The higher up I go on our planet, the greater the gravity is on the object. Another example would be these two skiers. You've got the one in blue and the one in yellow. Right? If they both go down the hill and they're the exact same weight, exact same size, and nothing changes other than the height that they're on, the height is what changes the increase of gravitational energy. When I look at the idea then of how we find gravitational energy, the book gives us that we're talking about weight times height. The reason we talk about that is because I need to once again understand the difference between a mass and a weight. Once again, mass is how much space is taken up. The weight is the gravitational pull, because if I am going to do this experiment and I hold that red ball out and I want to measure its gravitational potential energy, and then I put my spacesuit on, I go and I'm walking on the moon and I try the same thing, the increased gravitational potential energy is going to happen on the Earth because there's very little gravity on the moon. Another one that the book talks to us about as we finish up here is elastic potential energy. And elastic potential energy is found in several different things. So it's called the stored energy, but it's either when the elastic part is stretched or when it's compressed. And a lot of people don't think about the compressed aspect when it comes to elastic potential energy, but it is actually found in both, right? So if I took a spring and I pushed it down really hard and let go quickly, it's going to bounce up and down, right? It's going to release the energy that I compressed. And the same way on the right, if I stretch it out real far and let go, it's going to spring back because I've stretched it out. So there's two different forms of elastic potential energy, one that can be compressed and one that can be stretched. When I think once again about a bow for a bow and arrow, that's an elastic potential energy from stretching. I have to be able to pull the string back and notch the arrow in order for it to fly. If I can't pull the string back, I don't have any potential energy and it's not going to go anywhere. So pulling it back allows me to have that elastic potential energy. Flipping a rubber band, exact same thing. I'm pulling it back, and as long as I don't let go, I don't get in trouble. But it also is just stored elastic potential energy. The moment I let go, I get in trouble, and the rubber band's going to fly. Compressing then, maybe you have seen these exercise tool for hands, and maybe you haven't. I know some of you like to have like those squishy things that you sit there and squeeze constantly. Same idea. You're squeezing and you're compressing with your hands. Down at the bottom of this exercise equipment, there's a coil, a metal coil, and it's basically a very short spring. So I'm trying to squeeze it together and press that spring together, and then when I release my energy in my hand, it bounces back. In our vehicles, we also have large springs. So if you know anything about vehicles, we talk about shocks and we talk about the struts. So there's a big spring that is around the axle area for your car. And basically what it does is it's compressed really tight so that when you're hitting a bumpy road, you're driving down a gravel road, you hit a pothole, then it's going to keep the tires from wobbling a great amount. Now, if they go bad, then you have a lot of loose tires and a lot of loose movement. But it is a compressed spring that we use on a regular basis for our safety and the well-being of our families and our vehicles. So that really wraps up what we're going to be talking about on the second half. And as I had told you yesterday, it was not going to take the whole class. So you either need to work on something else. For my homeroom, that would be reading, that would be writing, that would be your all about me, that would be your math. For Mrs. Reiner, that could be your HMH, your math, or any other assignment she's given you. Or you can ask Miss Miller for the worksheet, and she has it, and she's ready to pass it out to you. Either way, you need to be working. And then tomorrow, you'll have all of class period to be able to complete your assignment. You need to be working. So make sure you have plenty of things. Make sure you do busy. And use your book to please prove your answers. Have a great day.